So we've worked with base E, the natural logs. Now we're going to look at some when the base isn't E. So when the base isn't E, that's going to be that regular log. Regular log has an understood base 10, unless it's written and it's an understood whatever it is. So that's why I've just got an A here. If it's not there, remember that's 10. Okay, I don't have it specified, so I just have an A there indicating that it's going to be whatever. Okay, what we do know is it's not E, because if it was an E, it'd be a natural log. Everybody okay with that? All right, now these are some pretty basic rules. There's not a lot going on. It looks a little confusing because you have this ln sitting in here. Right, so technically, okay, here's what you have seen. The derivative of ln x is 1 over x. Of course, chain rule could apply, but there's our old rule. Does everybody agree with that? Technically, I lied to you. That's not really the derivative. The derivative is technically this. 1 over ln e times x. But what's the ln of e? 1. Where did the e come from? Base. Is that e? Our other rule. The derivative of e to the x was e to the x. Easy one, right? Probably the easiest derivative rule we've had. But I lied to you. It's really this. Because that base is e. But what's the natural log of e? 1, so it goes back to e to the x. So that's why we can make the leap to these two. It's because this is canceling out. Okay? So this is really the derivative, but technically this is there. Cancels out because it's 1. Now we don't have e's. So there's your a to the x, ln of the base. Because that's not an e this time. So I get ln of something else. And that ln of something else is not 1. So not canceling out like it did right here. I'm showing it to you this way because this might make it a little bit easier for you to remember. That ln's there on both. We cancel it out over there because it's not going to matter. It's just times 1. Here it's not. Look at the log. Derivative of log was 1 over x. Well, it's still 1 over x. Pretend that's not there. I have a different base, so there's that ln of the base, which did cancel out over here just because that's 1. It's still really there. Are you okay with that? Right. And the same thing happened to the integral. You should remember the integral of e to the x was e to the x plus c. Technically, it's not e to the x plus c. It's really 1 over ln of e to the x plus c. But that's 1 again. So now when we have these different bases, again, different, something other than e, it doesn't matter what the number is there, we're going to have the ln of that value, and it's not canceling because the ln of that value is not 1. I don't know what it is, it depends on the value, but I know it's not 1 because it's not an e. Are you okay with that? So these are really, this is what we've done. This is what we have now, and the base is an e, really the same formulas. A little bit different look with that natural log. I'll show it back this way because sometimes students are pretty good dealing with these three. Oh, this was just e to the x. and then dealing with these three separately. And sometimes about half the students, and I did when I was first doing this, find it easier thinking of, hey, that ln. So that'll remind me to put that ln. Just kind of depends on you. I remember this better than this, mainly because when I first did it, because I'm old, it looked like that. There wasn't a natural log. A simplified function. So I was used to always putting the regular log with a base of e sitting there. And then I'd have a regular log with the base of e, which still goes to 1. Something like that. So you get a little bit different looks now. So you guys thought that'd been around forever, huh?
What's the main difference between the log and natural log?
What's that?
What's the main difference between log and natural log?
There's not. The natural log has a base, and a regular log, a base of e. A regular log doesn't. That's it. So here is, just make up some number. Doesn't matter what the number is. Okay. Pre, like 1985. After.
Gotcha.
And I'm 50, so when I was doing it, that's what I was seeing. Something like that. So that's really the only difference. So what it allowed them to do, around that time you came out with scientific calculators. Now you can program the calculator with 2 different things. Common base of 10, common base of e. It's pretty easy to program now and add whatever in because memory's cheap and easy. But if you wanted a calculator to do an infinite number of bases back then, it'd be as big as your desk. You know, things are different now. So they created this, 2 common ones, and so then this came about. That base of e. So still, even back then, the base e was the most popular. It's that exponential growth, decay, still the most used. It's really what happened. But we just simplified the form so we can get a button on a calculator for that piece. That's really it. They're the same thing. That's why the properties are the same and everything else for that piece. All right, so let's look at some of these. Remember, taking the derivative, chain rule still applies, right? So chain rule off of this x is 1. Chain rule off of that x is 1. Nothing really different there. All right, so let's say we want the derivative with respect to x of 2 to the 5x. So that's going to be ln 2 to the 5x times 5. Now, if you think back to what you did with the e's, if you take off that ln of 2, it really looks like the same thing. There's my exponential chain rule. Since it's on an e, I've got ln of 2 in front instead of ln of e. Are you okay with that? Now, a lot of times we'll see the 5 move to the front. Right, we're forced to have the parentheses in here, otherwise it looks like ln 22 to the 5x. We're kind of forced to have that. I don't care if you have the 5 at the end or not, but a lot of times we'll see it like this. Bring that 5 into the front. And you could even take the 5 up. This would be 2 to the 5th, so we could even see ln of 32. Like that. Different forms, just by your properties of logs. This would be that raw form that you're expected to get quickly. Got my natural log, my exponential chain rule. And then if you see some things written a different way, maybe just think about what happened. Right? But that raw form's that most important. If we can get that part, we can deal with the simplifying. That's the way it's been all along. If I had the derivative with respect to x of 3 to the negative x, I know it's going to be ln of 3 because that's my base. And here comes that exponential piece. Very similar to what we have with the e. We're going to see that 3 to the negative x again. Times the chain rule, negative 1. Are you okay with that? So let's go with the derivative. This time of the log of 2x. So when I take the derivative of a log, it would be 1 over whatever I was taking the derivative of, in this case 2, or whatever I was taking the log of, in this case 2x. What's my base this time? 10. It's not written as 10. So we're going to have 1 over, there's that ln of 10 down there. There's my 2x. So still 1 over what I was taking the log of, 1 over 2x. And then chain rule 2. Okay there? 2's would cancel. So I really just have 1 over ln 10 times x. Pretty good there? Derivative with respect to x, log base 5 of x squared. So since I have a base of 5, that's going to be where that ln of 5 comes in. So for me, I usually just go ahead and write it down there. Then I just deal with my derivative of the log. So it's going to be 1 over whatever I was taking the log of. In this case, x squared times the chain rule, 2x. And then we could have an x cancel there. Are you okay with that? Okay. How about this? Derivative with respect to x, log, we'll go base 7 this time, of x squared minus 4 over x. Now I know I'm going to have an ln 7. That's going to be sitting in there. That's not a big deal. It's going to be 1 over this times the derivative of this. So this is where we had a choice before. We can still use our log properties and split this up, or I can leave it together and do a quotient rule. Which would you rather do?
Split it up.
Split up, okay? And that's fine. Yeah, split up, it'll look like this. Minus log base 7 of x. I just have 2 pieces I'm working with. And that's where you're just kind of going off of which would you rather deal with. I don't think that one way is necessarily less work than the other. Okay? But you've got to go with what looks best for you. So in this situation, I'd have 1 over, there's my ln 7, of x squared minus 4 times 2x minus 1 over, excuse me, and there's my ln 7 again of x, and then chain rule is just 1 on that one. Everybody okay there? Nothing cancels here. This answer looks good. Yes, you could get a common denominator and put it together if you want going further. We've written out that piece. So same kind of log properties apply with those regular logs that we talked before about with natural log. Nothing new on there. Okay? They were logarithmic properties. They weren't dependent upon a base. Everybody okay there? All right. Now, when we did the integral of e, the key on the integral of the e to the x that we did was this guy was a nice single variable. Okay. So if I had the integral of e to the 4x dx, I had to do the u substitution on that 4x to get that single variable. That sound familiar? Same thing happens when you have this a to the x. I need that single variable right there. So if it's not a single variable, I'm going to have to do a u substitution. So if I had integral of 5 to the x dx, well, that's a single variable. I don't need to worry about a u substitution. I see just the x. So we'd have 1 over ln 5 times 5 to the x plus c. Again, the new piece is, or I say new, is I've got that ln of 5 down there. It was ln e, but ln e canceled to 1. That was a value of 1. So I guess new, not new. Same thing. Now let's change this x. Integral 3 to the negative, let's go negative 2x dx. I'm not worried about the 3. The 3 is going to produce a 1 over ln 3 right there. I'm not worried about that. What I'm worried about is that negative 2x. That needs to be that single variable. There's the u substitution. So we're going to let u be negative 2x. Du then would be negative 2 dx. Nothing new on the u substitution. We're going to have to, not subtract, divide by that negative 2. Out in front, right? So I would have negative 1/2 integral 3 to the u du. Get rid of my negative 2. Negative 2x is u. There's my u value. So now I'm going to have negative 1/2 1 over ln 3 3 to the u plus c. And I would encourage you, especially in your notes and in the beginning here when you first do the work, write this long form out. All right? I know that they'll mix the 2 in with the right in front of this ln, but write the long form out so you know the negative half was out in front, and the rest of it was just dealing with this guy. So now we'd have negative 1/2 1 over ln 3. 3 to the negative 2x plus c, because I'm bringing that u value back in. The only thing that really looks different here is this fraction right here, because the base wasn't e. Just using the ln of whatever the base is. Pretty okay there? All right. Let's see.